I am Dr. Satyabrat Maiti. In my previous resonance lecture series, I have discussed introduction and how to draw resonance structure. Today topic is resonance energy. Resonance energy of a compound is measure of extra stability of the conjugated system compared to corresponding number of unconjugated system that where same number of double bond is present. Now, what is conjugated system and what is unconjugated system? In conjugated system, double bond, single bond, double bond, and in unconjugated system, there is isolated double bond. Okay, so here it is butadiene, here it is ethylene. Now, this resonance energy can be calculated from experimental measurement. So now we can compare butadiene with two ethylene molecule 1,3-butadiene. This is 1,3-butadiene, and we'll compare 1,3-butadiene with two ethylene molecule. In 1,3-butadiene we have two double bonds, and in ethylene we have one double bond. So it is expected that energy of butadiene will be comparable of twice of two ethylene molecule, but it has been observed that energy of butadiene is less than that of twice of one ethylene molecule. So why it is happening? And in similarly energy of 1,3-cyclohexadiene is less than that of energy of 1,4-cyclohexadiene. In 1,3-cyclohexadiene we have two double bonds, that is conjugated, and in 1,4-cyclohexadiene we have two double bonds, but those are isolated double bonds. Now we'll show how we can prove that above inequation. For this, we need to know heat of hydrogenation. An organic chemist uses heat of hydrogenation data to measure the stability of carbon-carbon double bonds also. Now, we'll give you some examples. That is, 2-butene. 2-butene has one double bond, and when it is going to reduce by hydrogen, it will get butane, and energy of 2-butene is E1 and energy of butane is E2. Now difference between energy of butane and 2-butene is delta E, and this delta E is heat of hydrogenation, and heat of hydrogenation is always negative, that is exothermic. Now I will give you a statement. And what is the statement? Statement is lower the numerical value of heat of hydrogenation, higher will be the stability. Why it is? What is the reason behind this statement? So lower, again I am saying, lower the numerical value of heat of hydrogenation, higher will be the stability. For this we'll take three hypothetical molecule, and we are considering that these three hypothetical molecule contains double bonds, and these three hypothetical molecules A, B and C, and they are going to reduce by hydrogen, and for ultimately we'll get X, it is completely alkene. Now A plus H2, and this is B plus H2, and energy level of B plus H2, and this is energy level of C plus H2, and we are getting X after reduction. Now this is the heat of hydrogenation for C, and this is the red is the heat of hydrogenation of B, and black is the heat of hydrogenation of A. Now just remember the above statement. So order of numerical value of delta is hydrogenation is delta H3 is less than that of delta H2, and it is less than that of delta H1. So C is most stable one, because delta H3 is the smallest one. Clear? So, and from the diagram it is clear that C is the most stable compound. Now we'll extend this concept to understand resonance energy. For this we'll draw a simple graph, and here it is cyclohexane and here it is cyclohexene. It contains one double bond, and heat of hydrogenation of cyclohexene is 28.6 kilocalorie per mole. Now what will be the heat of hydrogenation of 1,3-cyclohexadiene where it has two double bonds? It should be twice of cyclohexene, but it is not. Here heat of hydrogenation for 1,3-cyclohexadiene is 55.2, which is less than that of twice of 28.6. That is twice of 28.6 is 57.2 kilocalorie per mole. But actually it is actual heat of hydrogenation of 1,3-cyclohexadiene is less than that of twice of heat of hydrogenation of cyclohexene. Now we'll consider a hypothetical molecule, that is cyclohexatriene. This hypothetical molecule, and why it is hypothetical molecule? It contains three double bonds, and three double bonds are isolated double bonds. They are not in conjugation with each other. And here the heat of hydrogenation is 28.6 times 3, because all three double bonds are isolated, and it is 85.8 kilocalorie per mole. Now we'll compare it with benzene. Benzene has three double bonds, but three double bonds are in conjugation with each other, and here heat of hydrogenation is 49.8 kilocalorie per mole. So heat of hydrogenation of benzene is less than that of heat of hydrogenation of hypothetical molecule cyclohexatriene, and it is and the difference between heat of hydrogenation of benzene and heat of hydrogenation of hypothetical molecule cyclohexatriene is 36 kilocalorie per mole, and this so benzene is stabilized by 36 kilocalorie per mole with respect to cyclohexatriene. So because it is due to resonance, so resonance energy of benzene is 36 kilocalorie per mole, because here three double bonds are in conjugation. So that is pi benzene involves in pi electron delocalization, that is resonance, and which gives stabilization. So that is how we have proved that resonance energy of benzene is 36 kilocalorie per mole. Thank you.